In the last lecture, we have discussed methods to find general solutions to linear and semilinear equations. In this lecture, we take the method one more step forward, namely to deal with quasi-linear equations. We are going to describe Lagrange's method for finding general solutions to quasi-linear equations. We start with a brief review of the last lecture, lecture 2.3, where general solutions to linear and semilinear equations have been obtained. Basically, a method was described. Now, we are going to describe in today's class Lagrange's method for finding general solutions to quasi-linear equations. How the ideas from linear and semilinear can be extended to the case of quasi-linear equations, whether it is possible or not, we are going to see, and which part of this method for linear and semilinear can be extended, which cannot be, we will see that as well. So, let us recall just to reinforce the notations. L stands for the linear equation Axy ux plus Bxy uy equal to Cxy u plus Dxy. SL stands for semilinear equation, where the left hand side is same as that of the linear equation. That means, the manner in which the first order partial derivatives appear is exactly the same. However, the right hand side can depend non-linearly on u, C of xy u. Now, QL stands for quasi-linear equations. Here the coefficients of ux and uy can depend on u also. So, A of xy u ux plus B of xy u uy equal to C of xy u, and the hypothesis that we will be working under is ABC are C1 functions and omega 3 is a subset of R3, open subset of R3, and as usual we require that both A and B do not vanish simultaneously at each of the points of omega 3. So, this is quasi-linear equation. As you observe, the first order partial derivatives, the coefficients in both L and SL, they depend only on x and y, whereas in quasi-linear equations they depend on u as well. This is the difference between semilinear, linear and quasi-linear equations. So, let us review lecture 2.3 now, where we have obtained general solutions to linear and semilinear equations. Basically, a method was described. Now, it is up to us whether we are able to implement it or not. That is silent upon, but it is possible, that is what the method says. Okay, what are the important steps in obtaining general solutions? There is a change of coordinates involved, xy to xi eta, because in L and SL both ux and uy appear. So, we thought that we will eliminate one of those partial derivatives, but ux and uy are there, x and y coordinates are there, coefficients AB are given, we can't suddenly make it 0. Then we thought, let us change coordinates and then find out if there is a possibility of finding change of coordinates, where after transforming the PDE, the new PDE in the new coordinates will feature only one derivative, maybe with respect to xi or eta, only one of them. That was the idea. Therefore, there is a change of coordinates in the background. Remember, change of coordinates works in xy plane, that is in omega 2, some subset of omega 2, there we have both xy and xi eta coordinates. And then we chose psi to be a solution of this linear homogeneous PDE, and then we chose a phi such that this Jacobian is never 0. Then the LHS of L and SL, which is this, now becomes this, it features only the derivative with respect to xi, and the PDEs will then become ODEs, which are then solved. That was the idea. Now, after changing the variables back to xy from xi eta, we get the solutions as functions of x and y. Now, how to extend this strategy to quasi-linear equations? A, B are functions of x, y only, they played an important role in obtaining change of coordinates. Therefore, the new difficulty in implementing this strategy is that for quasi-linear equations A, B are also functions of the variable z. So, this results in nonlinear PDEs for psi equivalently phi, because as we observed the equations are the same and only one of them is useful. So, we can only find one function, because if you choose both phi and psi as solutions of the same equation, then we will get that Jacobian will be 0. So, that is the reason we chose psi first and then we choose phi as anybody such that the Jacobian is non-zero. So, now it is clear the new difficulties. A, B depend on x, y, z unlike L and SL. This we are mentioning for the completeness sake, in the sense that phi psi satisfy nonlinear PD, but it is useless because change of coordinates now have to be done in x, y, z coordinates, not in x, y. But the PDE is only in x, y variables. So, therefore, we do not expect change of coordinates can be done. Therefore, in what other way we can extend the strategy? Let us discuss that now. In L and SL, psi was chosen such that psi equal to k represented a one parameter family of solutions to dy by dx equal to b by a. This is what we did, right. Now, in the quasi-linear case, what happens is b of xyz, a of xyz will come. So, necessarily we have to bring in some equation for z, we will come to that. So, psi of xy equal to k represent base characteristic curves. Okay, this is the equation for base characteristic curves after eliminating the parameter t. Therefore, for quasi-linear equations we can't determine base characteristics directly, that we know, because of the presence of z in both a and b. So, for quasi-linear equations looking at characteristic curves is thus natural. So, this is the way we are going to extend the ideas. We are saying that for linear and semilinear, looking at base characteristic curves helped us in obtaining a general solution to L and SL. For QL we have to look at full characteristics. So, non-parametric form of the equations for characteristic curves, this is after eliminating the parameter t, is dy by dx equal to b by a, dz by dx equal to c by a. This is the idea of Lagrange's method, but no change of variables as expected. So, let us now describe Lagrange's method for quasi-linear equations. So, Lagrange's method, the main idea is this. Before we present that, we will assume that A is never 0 on omega 3. Okay. So, Lagrange's idea is to consider the two parameter family of characteristic curves corresponding to quasi-linear equation given by dy by dx equal to b by a and dz by dx equal to c by a. These are the equations of the characteristic curves. Assume that the two parameter family of characteristic curves are given by intersection of two families of surfaces phi of xyz equal to c1 and psi of xyz equal to c2. This is the assumption. Okay. We will see in examples that we can get this. So, finding really the phi and psi is the most challenging part of this Lagrange's method. Okay, let us state the theorem of the Lagrange's method. Assume that phi equal to constant and psi equal to constant represent characteristic curves for QL, and grad phi and grad psi are never parallel to each other. At all those xyz which satisfy both these equations, at those points grad phi is never parallel to grad psi. Let f be an arbitrary C1 function defined on R2 such that f xi square plus f eta square is not equal to 0. In other words, the gradient of gradient of f is never 0 at every point in R2, because domain of f. Okay. If you do not have R2 here and some domain of f, then we require this for every xi eta belonging to domain of f xi comma f eta is not equal to 0 0, they do not simultaneously vanish. Assume that f of phi of xyu comma psi of xyu equal to 0, this equation defines a C1 function xy mapping to u of xy. That means, this is an implicit equation for u, and that can be solved. U can be solved in terms of the other two variables. For x y belonging to some open subset of omega 2. As usual, we do not demand that everything should happen on omega 2, because typically the existential results which deal with such assertions is implicit function theorem. That is once again a local theorem. So, for x y belonging to an open set, we demand that f of phi of x y u comma psi of x y equal to 0 gives rise to a function u of x y. Okay, if f phi psi are C1, automatically u will become C1. Okay, that is we are discussing now whether you can always assert this, that is implicit function theorem, but as far as this theorem is concerned, we assume that such a thing exists. Then u is a general solution of the quasi-linear PDE QL. First observation is ABC is parallel to grad phi cross grad psi. Observation 2 is such a PDE is satisfied. Okay, what is grad phi cross product with grad psi is this. Okay. In other words, this is this, right, this is the first component, this is the second component, and this RHS is the third component. Okay. If this is parallel to ABC, what does that mean? This vector is some constant times ABC. Therefore, let us say alpha ABC. So, you can substitute this is alpha A, this is alpha B, this is alpha C. Cancel alpha, what you get is AUX plus BUY equal to C. So, therefore, these two observations prove the theorem. So, therefore, the proof of the theorem follows from the following two observations. So, what remains to prove is these two observations. Observation 1, what is observation 1? ABC is parallel to grad phi cross grad psi. So, phi equal to C1 and psi equal to C2 describe characteristics curves for QL. This is the assumption. What does that mean? It means that given any characteristic curve x t y t z t parameterized by t belonging to some interval j of r, x t y t z t satisfies both the equations. What are the equations? Phi of x t y t z t equal to C1 and psi of x t y t z t equal to C2. It lies on these surfaces. Okay. That is the meaning of saying this and this together describe characteristic curve. It means if you have characteristic curves, they lie on the intersection of these two surfaces. So, it means that there is a C1 and C2 such that phi of x t y t z t equal to C1 and psi of x t y t z t equal to C2. Now, once we have this, we differentiate with respect to t both these equations, and we will get ABC dot grad phi is 0 and ABC dot grad psi is 0. So, this is what we have, but grad phi cross grad c is not equal to 0, that is what we have assumed. Therefore, ABC must be parallel to grad phi cross grad psi. If a vector is orthogonal to two vectors, let us say u dot v is 0, u dot w is 0, then u is parallel to v cross w if v cross w is non-zero. So, we have used that and we concluded ABC is parallel to grad phi cross grad psi. This holds at every point x t y t z t on the characteristic curve. So, this is the notations we have used. This stands for this particular determinant. This is the Jacobian of phi psi with respect to the variables y z and so on. Observation 2. What is observation 2? Observation 2 is such an equation is satisfied. This equation is satisfied. Let phi and psi be C1 functions. This is how we write phi is defined by phi of x y z just to denote the variables for the function phi. Later on we are going to substitute in place of z u of x y, but this is the function of 3 variables. So, it is defined on an open subset of R3. It is very much useful when we apply chain rule, so that we do not have confusion. So, f from R2 to R be an arbitrary C1 function, and we denote this by f is f of xi comma eta. Assume that this equation defines a C1 function, that was part of the assumption. Now, differentiate this equation with respect to x and y. So, if you want to differentiate this equation with respect to x, x is present in both of them, therefore, differentiate f with respect to xi at this point phi comma psi, which are the arguments I have not written, then differentiate this with respect to x, but here x appears here in the first coordinate and also in the third coordinate. So, differentiate phi with respect to x plus x with respect to x is 1, that is why it is phi x, plus phi with respect to the third one, the third variable we have denoted by z. So, it will be phi z into u is there, differentiate u with respect to x. So, you get ux. Similarly, you differentiate here also, you get f eta, because the second variable of f was called eta. So, f eta at this point into derivative of psi with respect to x plus derivative of psi with respect to the z variable into derivative of u with respect to x. That will give you the first equation here. Similarly, we get the second equation if you differentiate this with respect to y. So, here we should have written u of xy and here u of xy. That is the meaning here, right. It defines a C1 function, that means I can substitute here u of xy, u of xy, and that equation would be valid on a subset D of R2. Okay. So, the system on the last slide, it is a linear system for f xi and f eta, okay, f xi and f eta. So, you write f xi f eta as one column, then this is the first row A11, first 1 entry, 1 2 entry, 2 1 entry, 2 2 entry. This is what we have. Now, we have assumed that both f xi and f eta cannot be 0 simultaneously, which means this system has a non-trivial solution, a non-zero solution. This homogeneous system, it has a non-zero solution. It means that the determinant of this is 0. And if you expand, this is what we get. So, one of the hypotheses of the theorem is grad phi is never parallel to grad psi. What does that mean? What is the geometric interpretation? For each C1 C2, the surfaces phi equal to C1 and psi equal to C2 intersect transversally, and their intersection cannot be another surface, because normals do not have the same direction, normals have different directions. Therefore, the tangent planes will have different directions at every point which is common to both the surfaces phi equal to C1 and psi equal to C2. At such a point, look at the tangent plane for phi equal to C1 and tangent plane for psi equal to C2, they do not coincide at all. That is the assumption we are making, that grad phi is never parallel to grad c anywhere. So, Lagrange's method provides a general solution implicitly by this relation, okay, because we assume that u can be solved for in terms of x y. In such a case, we define that to be a general solution, where f is arbitrary function. We have to just make sure that phi and psi take values in the domain of f. If we have taken f in R2, then we do not have to take even that much care. Once phi and psi have been determined, this is where the catch lies. This itself is the drawback of the method, finding phi and psi. Let us look at an example. Using Lagrange's method, find general solution to this PDE, xux plus yuy equal to u. Actually, this is a linear equation. Okay, characteristic ODEs are given by this is another way of writing dx by dt equal to x, dy by dt equal to y, dz by dt equal to z. Or since t is not present, this is another way of writing dy by dx equal to y by x, dz by dx equal to z by x. So, you integrate dx by x equal to dy by y, you get log mod x equal to log mod y plus constant for some constant, and that gives us that mod x by y is e power k, and that implies x by y is C1 where C1 is non-zero, because e power k will never be 0, right, no matter what k is, e power k is never 0. So, x by y equal to C1. Similarly, on integrating the other equation dy by y equal to dz by z, we could choose any combination. Okay. We just want two functions phi and psi. Okay. So, this is one solution, x by y equal to constant. It is a solution of this particular equation dx by x equal to dy by y. Now, we will look at dy by y equal to dz by z, we get similarly y by z equal to constant. So, now what we want is phi and psi, so that phi equal to C1, psi equal to C2 together represent characteristic curves. So, now by Lagrange method says f of phi comma psi equal to 0. So, therefore, this represents a general solution. Let us look at another example. Unfortunately, this is also linear. We will discuss some quasi-linear equation in the tutorials. So, characteristic ODEs are given by dx by y minus y equal to dy by x, dx by a, that is minus y, dy by b, that is x, dz by 0. Now, on integrating this equation, we get x square plus y square equal to constant, C1 positive, and integrating this we get z equal to constant. Therefore, Lagrange's method says general solution is given by f of x square plus y square comma z equal to 0, f is arbitrary. If I take a specific choice of f, which is eta minus g psi, what I get is u equal to g of x square plus y square. In other words, this solution, if you observe, this is constant on each circle with center at origin, x square plus y square equal to constant, positive constant will give you u is constant on all circles with center at the origin. Please note that if you have integrated this differently from what is done here, you will get f of some other two functions equal to 0, and those two functions, these two functions will be related somehow. Okay, they will be functionally dependent. I do not want to use these terms and discuss this further, but as long as you get phi equal to constant and psi equal to constant representing characteristic curves, capital F of phi comma psi equal to 0 will always represent a general solution, provided we can solve for z in terms of x and y. For example, if I chose this f, of course, this is solvable, u equal to g of x square plus y square, where g is an arbitrary function. So, let us summarize what we did in this lecture. In lecture 2.3, linear and semilinear equations were transformed to ODEs by a change of variables. General solutions were obtained. In this lecture, Lagrange's method to solve QL was presented. How ideas from simpler cases of L and SL extend to QL were looked into, and we have presented two examples to concretely illustrate the general algorithm which is given for finding general solutions to QL. And we cannot do this kind of general solutions to nonlinear equations. So, beyond QL our theory does not go. So, to solve even such equations, we will try to solve using what is called method of characteristics. In the next few lectures, we will be presenting the method of characteristics and its preliminaries initially, and then we use that method to solve quasi-linear equations first, and then once again extend those ideas to solve general first order nonlinear equations. Thank you.